Here we have two tangent circles with centers A and B. And as a property of tangent circles, the point of tangency right here is on a segment AB. Now what we're going to do is we're going to draw diameters through points A and B, and those diameters are going to be at 90 degrees to the segment AB. Those diameters are going to intersect the circles at points C, D, E, and F, and we're going to draw a circle through those 4 points. We are asked to find the red area, and that is the area of the big circle that is not occupied by small circles. And we are given a piece of information, that is the area of the small circles that sits outside of the large circle. First, notice that the center of the big circle, point O, is on a segment AB. Well, it can be shown a couple of ways. One way is to simply see that there's a symmetry, horizontal symmetry in this picture with respect to segment AB. The other way is to simply connect point O and D and notice that COD is an isosceles triangle and the segment AO is the side bisector and the altitude at the same time. The next thing what we're going to do is to denote CO and EO with big letter R. That's the radius of the big circle. Now the side AC is the radius of the left circle. We're going to denote R1. And the radius of the right circle, the segment B, we're going to denote as R2. Also, segment AB equals to R1 plus R2. And segment AO we're going to call X, which we're going to find afterwards. And from that we also can find OB as R1 plus R2 minus X. The next thing is to notice that we have two right triangles, this triangle ACO and this triangle BEO. And we're going to write Pythagorean theorem for both of those triangles. So for the first triangle, we're going to get expression like this. For the second triangle, we're going to get expression like this. So for the second expression, we're going to open up this parenthesis, and this is what we're going to get. Now we're going to subtract the first equation from the second one. And if you do, this is what we're going to get. On the left, we had R squared and R squared. We get 0. Now, R1 squared and X squared are going to cancel out. Now notice there is R2 squared and another R2 squared. That's why we got 2 R2 squared right here. The next thing to notice that every term here has a factor of 2. So let's divide this equation by a factor of 2. That's what we're going to get. And the next thing is to notice that the first two terms have a common factor R2, which we're going to pull out. And the second two terms have a common factor of minus X. We can also pull it out using distributive rule. And this is what we're going to get. Now notice that we have R1 plus R2 or here and here. R1 plus R2 is non-zero, so we can divide this equation by R1 plus R2. And when we do, we get this expression that really tells us that X equals to R2. Now we're going to plug this value of X into the first Pythagorean theorem here. And that's what we're going to get. And the next step, let's multiply this equation by pi. What this means is that the area of the large circle equals to the sum of the area of the small circles. And that also means that those green areas that are sticking out from the large circle are equal to the red area. formally we can show this that the red area equals to the area of the large circle minus the left white area, that's the first parenthesis, and minus the right white area, and that's the second parenthesis. So left white area is the area of the left circle minus 9, and the right white area is the area of the right circle minus 5. So since pi r squared equals pi r1 squared plus pi r2 squared, we find that all the terms with pi cancel out here, and all we have left is 9 plus 5 equals to 14.